Hello, welcome again to the lecture series on automobile engineering. In the last two sessions, we have discussed about automotive suspension system. So we continue our discussion on suspension system. In this session, let us discuss about passive and active suspension system. So first question is, what do you mean by passive suspension system? So, you know that I represent the suspension. Suppose this is the sprung mass and this is the unsprung mass, and between these I showed the suspension. Right, and I call this as Kt, tire stiffness. This I called it as Ks, suspension stiffness, and this I called it as suspension damping. So when we design the suspension system, of course we take many factors into considerations. One of the main factors that we take into consideration is the natural frequency of the sprung mass. It is given by 1 by 2 pi, say root of Ks, suspension stiffness, divided by sprung mass. And we'll try to fix this value approximately equal to 1 Hertz. So then we arrive at the Ks value and design a mechanical spring accordingly. So now its value is fixed. So many kilonewton per meter. Okay. But in reality, you see, I must have designed this for a laden condition, that is loaded condition. By chance mass varies, means say unladen condition, or there is less mass, definitely this value will change, frequency will change. So resonance frequency will change. So then the comfort levels will change. These are the kind of problem we will face with a fixed value of Ks. It is desirable, depending on the driving conditions, that if you can vary the value of Ks, we can achieve the required occupant comfort in a car. Let us consider the damping. So normally I said we'll use a dual rate damper. As I mentioned, there are two strokes, that is bounce, that is expansion, jounce, that is compression. I think I have messed it up in the previous video. I would have said other way. I think this is correct. Jounce and this is bounce. Okay. During this stroke, we'll have a damping value of say 0.2. This will have a damping value of 0.4. But let us see, depending on the condition, even the damping value must change. For example, your car is running on a level road. So when it is running on a level road, it is necessary that we make the suspension soft. Otherwise, this will not reciprocate at all and dissipate the energy, and that may create a lot of uncomfort. So this has to do that. Even the spring has to be soft. Correct. Now the question is, like, you are climbing up, so it needs to be hard. Again, it is you're climbing down, you are running at a particular speed. If it is too hard, then the suspension will not respond. Then it may lose the road holding. That time it may become, say, medium. Okay, that is damping coefficient, and Ks must be something different. It should not be too hard like this. It is desirable that we change Ks value, so also the damping value, depending on our requirement. But in our traditional suspension system, they remain constant. Such a system, we call it as a passive suspension system. Correct. So that's what exactly I said, like, during the Jones stroke, see here, should be around 0.2, this should be around rebound stroke, or bone stroke should be around 0.4. That's how the damping value will be. And mainly the damping which I explained earlier. Because of this here, so here we'll have orifices. When the oil passes through these orifices, then only the dissipative effect is created, which I have explained earlier with the help of Newton's law of viscosity. So the behavior of these, or the characteristics of this, are shown here. Air force into velocity, damping coefficient is given by damping force by piston velocity, Z dot. So this is force, this is velocity. Here, characteristic A, if you see, at slow piston rod speed, fluid passes through a predetermined orifice area in the valve seat. Valve seat is the predetermined area. So here, force versus velocity character, you can find this. Low velocity, high force, damping is very large here at low speeds. Slow speeds, you can find very large damping, because this, if you measure the gradient, this force and the velocity. Velocities are small, force is large, damping coefficient is large. And other one, if you look at the B, at medium rod speed, fluid is controlled by discs which act as flat blow-off springs. The characteristic is shown like this. Again, very, very low speed, the damping coefficient is large, but as the speed increases, damping coefficient almost becomes very, very small, right? That is the thing. So C, at high speed, the fluid is controlled by the orifice slot area in the valve seat here, and this is the characteristic. You get almost a linear characteristic like this. So depending on the speed, this is behaving, and you get at different velocities, like you can find out the damping coefficient. Probably the medium speed, you can see here, it is something this way. Other, it is working almost linearly with velocity, the damping coefficient value. Okay, that's how it works. So now the question is, look at this. Now we have, as I mentioned, consider our model. Okay, right, sir. If you consider our model, this is our KT and this is your KS. So this ratio is nothing but KT by KS. This KT by KS ratio is small, means this is hard spring. As this value increases, that means it is soft spring. Okay, now here RMS vertical acceleration of a sprung mass. These accelerations I am talking about. Sprung mass, vertical acceleration versus suspension travel. These are given for different values of tire and stiffness. So like suspension, tire stiffness by suspension stiffness. You can see here when the RMS suspension travel is low, then the vertical accelerations are high. As you go on increasing this, this is coming down, the accelerations are coming down better now. But again, suspension travel is larger. Then again acceleration increases. This is how you can find the characteristic. So for this given tire and tire stiffness by suspension stiffness, probably this lower vertical acceleration you can find in this region. So lower the vertical acceleration, better. The reason is the force transmitted to the occupant, if you want to find, let us say the mass of the occupant and the acceleration is subjected to. If this acceleration is very high, you will be subjected to very high force. So that means to say, definitely it creates a lot of uncomfort as an impact. Okay, so if I can make suspension spring softer, it is coming down like this. But you can see here increasing damping, you are increasing the damping also. So you are making the spring softer and probably increasing the damping means damping value you are increasing, definitely responsiveness will increase. Okay, so somewhat this becomes a kind of usable range. So depending on the road condition, you might have to take this position or take this like this, and accordingly adjust the damping value and maintain as far as possible low RMS vertical acceleration values. So now the question is, can we further decrease this? Correct. These are all the questions come like this. So that the acceleration is minimum, comfortable will be very high. Now, if you can vary the stiffness ratio, if I can vary the damping, then I can achieve the required result. Let us say, what are the damping requirements? Damping requirements. Here I have written control objectives, damping force, front and divided by rear, front by rear. Roll reduction for quick steering operation. Hard. So if you see the front view, roll happens about x-axis. This is the x-axis of the vehicle. When you steer it, this is outside, this is inside. There will be large lateral accelerations. This is steering. Then there will be load transfer like this. So, if you take the suspension left and right, correct? See here, this is the axis. This way it will be there. So you want to create some kind of anti-roll effect. It is better that we increase the stiffness, increase the damping, like this. So it means to say, you move in the curve somewhere, here. So you require hard. Similarly, when you are pitching, you see here again, if you look at the side view of the car, this is y-axis, this one is x-axis. Again you say front suspension and the rear suspension. Okay, so it says braking. That time load gets transferred like this. So this will dive. Correct. So you want to avoid that. You should create reaction like this. It should be hard. Okay, reduction of pitching when acceleration is same idea, like when accelerating. When accelerating, load gets transferred like this. Okay, so this is what is necessary. Sorry, this kind of thing. Bouncing, that means vertical movement. Okay, vertical movement. So it is necessary, otherwise we want to reduce the acceleration, so keep soft. Road holding. So road holding in the sense, right? Let us say something when the vehicle is here, the whole suspension will be in the compression state. Correct. If the vehicle is moving, then the suspension what we have here, that is spring and a damper, respond fast and be in touch. The wheel should be in touch with the contour. If I make it too hard, it may not respond. What do we mean by that is, suppose you have a system, I model it and study its second order response. Suppose it responds like this. You see here, this is response versus time. Okay, so this time will be shorter. If I make this damping very high, then it may respond like this. Then it is going to be too much time. So road holding will not be there. Then the wheel take too much of time to touch the ground. It will be in the air for some time. So that's why you have to be careful. We have to make it, softer. Road holding performance, it is given over here, medium by medium. So these are stability improvement at high speed, medium, and soft. Front medium, and here in the back soft like this. So there is question of what it means is like understeering or oversteering, whatever can happen like this. So depending on the condition, the values should change. So that is the need for active suspension system. But in the present, we have two types of design. One is called semi-active and the other one is called active. As I said, there are two things here, stiffness and damping. In a semi-active suspension, we'll try to change only damping coefficient, keeping stiffness same. In the active suspension is basically some of these two forces, suspension as well as stiffness force, that itself we control. Okay, this is what we call it as semi-active suspension and active suspension. So we use a set of sensor systems to predict the road condition and at what time the vehicle may go and hit that obstacle. All these things we can predict. Means we sense this and send it to microcontroller. The microcontroller, as per the program logic, it will decide this. Then it will make a decision based on that, what should be the damping value of that, and changes the damping coefficient of this shock absorber. So that's what happens in a semi-active suspension system. But it is not going to work on the stiffness of the spring. Here, no, decide what should be the force, and accordingly the force is controlled. Okay, this is the basic principle. Now, you see here, you have the vehicle steering angle. So when you steer the vehicle, it will indicate from that steering input is given here to the ECU. Then it understands the intention of the driver, in which direction the wheel is or the vehicle is heading to. Vehicle speed will give an idea, lift, drive, whatever. Vehicle speed gives you in what time these wheels may go and hit that obstacle or conditions. Then whether you are braking or not, correct, whether you are accelerating. So all these kind of inputs are given so that the ECU, electronic control unit, as per the logic, can calculate what should be the damping and stiffness value. Accordingly, it can send signal to each one of the suspension system. Correct? That is the idea. It is each one of the suspension system it can send to maintain the required condition. Imagine your vehicle is running with something like 100 kilometers per hour, and what the time available for sensing, processing, sending the signal, and activating the system. Okay, it all should happen. That is the way the control system needs to be designed. Already I mentioned this is the usable range. If I use active suspension, I can reduce the range. Correct. Very, very low RMS accelerations can be maintained. So this already I told you how the damping effect happens and the damping coefficient model. So many technologies are available to vary the damping coefficient depending on requirement. Okay, one of them is your Magneto Rheological fluid. So they call it as MR fluid. Basically, MR fluid is prepared using iron particles of 3 to 5 micron size, and there will be a carrier liquid, is hydrocarbon oil, and also they put the additives to avoid the settling down of the iron particles. They all mixed like this, and you will get the Magneto Rheological fluid. It's a special way of preparing. Now, what exactly happens is that the viscosity of this fluid can be varied by passing a current. So in this fluid, when we pass the current, its viscosity can be varied. Rheology. Initially in the liquid state, as the current passes through this, around this conductor, a magnetic field will be created, and that magnetic field will align the particles. How closely it will bring the particles, how it aligns depending on the rheology changes. And that change in turn depends on the current. By controlling the current, it is possible to control the rheology of this. So this has become very, very popular nowadays. This they use in car suspension, seismic protection of building, cable stayed building, household application like washing, prosthetic knees, artificial muscles. All these applications they use. Has become very, very popular. Okay, even people are thinking about using in brakes, hydraulic valves, okay, gun recoil protection, and so on. This is what I said earlier. You can, passing the current, you can align this. You consider your conventional damper. Here you have the rheological fluid. Suppose you have the electromagnetic coils over here. If you pass the current, based on the current value, the rheology of this changes. So that when the piston moves through this, so as I said, damping coefficient is force by velocity. If this viscosity increases, force increases, and damping coefficient also changes. So like this, if you align more and more, and you can go on making it very, very hard. If you reduce the current, we can reduce the viscosity also. But where to keep the coil? There are so many ways of doing it. Some people keep the coil here itself, so that as it passes, rheology of the fluid can change, accordingly damping coefficient can change. So these are some of the work done, how exactly when the current passes through this coil, the magnetic field changes, accordingly the particles get aligned. And this is force versus velocity characteristic for different current values. So you can see here you have the force value here versus velocity value here. Correct. At any point you can find the damping coefficient. Damping coefficient of this. So you can look at the YouTube videos, many are available, understand how exactly MR fluid damper works. So you can connect it to all the four wheels like this. Here MR fluid damper, front, rear and all that. Okay. Now the question is like you can use various sensor systems like speed sensor, steering position sensor, supersonic sensor. Since the steering sensor will give you in which direction your vehicle is heading to. From speed sensor I can make out at what time, what is the time available for this wheel to go and hit that obstacle. From supersonic sensor I can find out the distance of that, and not only that, the shape of that also I can get an idea. So once we get all these ideas from the sensor, and this sensor information is given to control unit. Correct. Control unit, I'll give this. Of course. Then this is a process. Let me not get into that analog signal conversion, and then it is becoming digital signals and kind of thing. Then these have to actuate the required actuators. Okay. These signals will go and actuate, decide what should be the current to be supplied. Correct. What current should go to this, and accordingly whether, depending on the table which I had explained, depending on the condition, they can change the rheology of these and make hard, soft, medium, depending on the requirement. As you have seen in the characteristic, the current value changes, the damping coefficient changes. So there is another technology that is available, semi-active suspension. As you have said, like it all depends upon the RFIs. So if you can control the RFIs depending on my requirement, the C value I can change. So I use solenoid systems to vary this position, valve stem position, and accordingly I'll open this RFIs. You can see here this type is the most economic and basic type of semi-active suspension. Consists of a solenoid valve which alters the flow of hydraulic medium inside the shock absorber, therefore changing the damping characteristic. Okay, the solenoids are wired to the controlling computer which sends them commands depending on the control level, varying the RFI size, varies the damping coefficient. So this is what happens here. So how exactly solenoid valve semi-active suspension works, that is also such videos again available on YouTube. Request you to type this keyword and watch the video. So now instead of this only varying damping, can we vary the complete force itself, that is stiffness force plus damping force together. That is what we call it as active suspension technologies. There are many such technologies available. One of them is pneumatic. Here you can have a liquid a hydraulic fluid, right? And hydraulic oil you can have. Here you can have air, compressed air. By varying the air pressure, also by varying this oil pressure, we can always vary the force to be imparted. That's the main thing. So sensors see the road condition. Based on the road condition, CPU calculates what should be the suspension force to be generated. Accordingly, suspension force is generated here. Suppose you require, this should be very hard. Pump in more oil, then this will become hard. Pump out oil here, then this air will expand, this will become soft. So that way we can go on varying this. Okay. So you must have seen many vehicles have this hydraulic ride height adjusting systems. You can see in this, right, moment you put a load over here, this will go down. Okay, you can see here it is going down, has gone down. Only thing is you have to lift it up. So to lift it up, what is that you have to do is, right, pump in oil. Okay, so it can lift this one. So here now the question is, it has to be made less hard like this. So you can see here it is going up, it will become, you're pulling this up. Moment I make this, reduce the oil pressure over here, it will go up like this. I think I explained it a wrong way. The correct one is, you see here, let me read out. Height corrector 3 admits hydraulic fluid, which, it will push this way, it will increase the length, lengthens the strut and raises the vehicle to its normal ride height. Okay, right. So, sorry for the, wrong explanation. Okay, how hydropneumatic suspension works, you can see from this video. There is what you can call it as air suspension control also we have. You see here, for each wheel, I have a compressed air supply system like this way. Okay. So depending on the requirement, which should become soft or which should become hard, you can see here, you have throttle position sensor to know you are accelerating or deaccelerating, steering sensor, direction, vehicle speed, as I've already mentioned, you can find out how far the obstacle is. Okay, so all these are there. These are all given to the ECU, this data. Based on that data, either it will supply air to this actuator or remove the air. You can see that a cylinder system everywhere. Here you can see. Okay, by supplying the air, I can raise this. Removing the air, I can lower this. Okay, for that I have the valves, whether to supply air or remove the air. and also depending on what ride height I should manage, all these facilities are available with this. Okay, so this kind of active suspension technologies are also used. I'm not talking very much in detail. Probably from the sketch itself, you can understand this working of this system. That's the reason why I'm not very much dealing in detail, because you see, you can also understand there is an air compressor here, then air is dried, then the dry air comes out here, correct? Then from here you can go to the front wheels, you can supply the air. So also you can supply the air to the rear wheels, correct? Either you supply the air or release the air. So depending on the suspension heights can be adjusted. That's what it means. Okay, how air suspension works. Now you understand this, how roll control is done in this case. You know, there is a roll center, and of course you have the centrifugal force. Then this whole thing is going to roll like this. So you need to create anti-roll effect. So increase this force, you see here, and this force into center of gravity distance. So also this one, this if you make it hard, it will not stretch back. So it will also pull in this direction. So that way, making this air supplying to this, releasing the air, or in the opposite direction supplying the air, we can hold this system horizontal. We can completely control a roll. So also the pitch. Correct. Suppose, assume that you are braking this vehicle. So load gets transferred to the front. Correct. Then it is pitching. So immediately you need to create a reaction like this. Make this hard or increase the pressure in a pneumatic system. This force and this distance will create a torque. So also you do it in the opposite direction. You create this and you can keep the system horizontal. That's how we can control the pitch, and you can control the roll. So also you can control the bounce. This diagram shows a power spectral density, means the total energy that is available in the spectrum. Okay, the energy is more, it will lead to more uncomfort. Energy is less, better. So cars with conventional suspension system, you can see here in this frequency range, correct, which is not, these are the right region, that's what it is. And this is the one which creates more uncomfort. You see here in a conventional system and all that thing, this is what you can see. But a car with a hydraulic active suspension system, this can be very much reduced. The acceleration values can be very much reduced. So it means to say you can operate somewhere this region, low acceleration, RMS acceleration values. Okay, so that way you can make things comfortable, and definitely occupants will enjoy the vehicle ride. Okay, and you can see here these are the characters: roll angle versus right turn acceleration or left turn acceleration. So conventional car, this is the roll angle that you experience, but if you have active suspension system, these are the kind of roll angles. So suppose 0.4 is the G value, then you can see here, this is what you can call it as roll angle that you experience, maybe less than 1 degree. But if at all, if you take conventional domestic cars or whatever it is, this can be as high as 2.3 to 4. That is the thing. So then you see the person who is sitting over here, you know, he'll be like this, subjected to rolling frequency. Then there is a roll frequency. And if this roll frequency, again, it is very much greater than maybe 1.5 hertz, that will definitely, he feels very, very uncomfortable. Same thing, if your pitch frequency is more than 1.5 hertz, then also the occupant will be very, very uncomfortable. So the whole idea is reduce this, right? Correct? Those frequencies, or isolate those frequencies. Okay, that is the whole idea behind this. So that gives you basically a technology that gives you a clear picture of the advantages of semi-active and active suspension system over conventional passive systems. However, design of these things, we talk about how to design all these things. In vehicle control systems, we talk about very much in detail. Okay, so interested people, how exactly all these things work, how to design, you can study automotive electronics textbooks and learn this. Okay, automotive electronics. So here the idea is of this course, just to give these characteristics. In those courses, I think I have dealt very much in detail about this. Okay, now thank you very much. I hope you have understood the basic concepts of suspension system. So that completes the lecture on suspension. In the next video, I'll be discussing another topic. Till then, thank you very much.